Hello everyone, in this lecture I'm going to talk about half-wave rectifiers with RL load. So first of all I will draw the circuit diagram. This is an AC source connected to a diode connected to an RL load, and an RL load can be, for example, an electric motor. As we know, the voltage of the source is expressed by this function V maximum sine omega t, and the input-output waveform relationship is shown in this graph. This is the input sinusoidal function. The output in an RL load as a function of time. This will be the voltage. It's a half wave. The negative half cycle is eliminated on the load side, while the current is different. The current will lags the voltage by an angle, theta, and then it will continue due to the inductance into the circuit. After the diode is off, meaning that this diode, like an open switch, the current will continue to flow because the energy storage into the inductor. So thus this will force the diode to turn on again and continue to be on until the current is zero. And we can express this relationship in this graph by a differential equation. If I took the Kirchhoff voltage law on this closed loop, it will be V maximum sine omega t, the voltage drop across the resistance, plus the voltage across the inductance. So how can we solve this differential equation? In this equation we have a forcing function and a natural response. So the natural response in this circuit is when the right hand side equal to 0, means Ri plus L di by dt is equal to 0. And the solution to this first order differential equation will be as follows. I will rearrange this equation to be di by dt. I divided all terms by L, so plus R over L I as a function of time is equal to 0. Then I will exchange this term by this term, meaning that this is di over di over I plus R over L dt is equal to 0. Now integrate both sides. So we will get integral of di over I plus R over L integral of dt equal to 0. Then we will get the integral of this one is ln I minus I at time 0, which is the initial current, plus R over L the integral of a constant dt will be a constant t, which is equal to 0. Now, since this ln is minus this ln of the initial current, then I can write it in such a way that ln I of t divided by ln of the initial current plus r over L t equal to 0. Now we will write the equation by removing this to the other side with a negative sign. So I of 0 equal to minus r over L t. Then taking e of x to the both sides of the equation here. So this will give me I of t over I0 equal to e to the power minus r over L t. So I of t is equal to I of 0 e minus r over L t. So this is the natural response of the RL load. Now to find the force response. Remember we had V maximum sine omega t equal to Ri plus L di over dt, and we found the natural response. The only thing we have to find is the forcing response for the sinusoidal input function. So this will tend to be the steady state current value, which is equal to, the current will equal to V maximum over the root 2 of r square plus omega L square times sine omega t minus the angle theta, which is the angle between the current and the voltage. So the total response for this system is I of t is the steady state value, which is r squared plus omega L squared sine omega t minus theta plus the forcing function, which is a, the theta is equal to tan inverse omega L over r, and tau is L over r, which is time constant. A is the initial current value, at t equal to 0. So if I took this equation and at time 0 the current, it is at the time at which the current will equal to 0, at time equal to 0 equal to V maximum over Z sine omega multiplied by 0 minus theta plus A, the constant, E minus 0 over tau. So 0 equal to V maximum over Z sine minus theta plus A, this is equal to 1. then A is equal to minus V maximum over Z sine minus theta, and since this is minus, the minus goes here and make it positive. So the total current as a function of time will be V maximum over Z sine omega t minus theta, plus A is V maximum over Z sine theta or tau. So we take this, V maximum over Z as a common factor, so V maximum over Z sine omega t minus theta plus sine theta e minus t over tau. So this is the current waveform as a function of time in the half-wave rectifier with RL load. Said the voltage waveform will be something like that, and it will end the conduction by an angle called beta. So we want to find what is the angle at which the voltage will be equal and the current will be equal to 0 again before the end of the period. So we have to put the current as a function of beta, so it will equal to V maximum over Z sine, we change omega t equal to beta, so it will be beta minus theta plus sine theta e minus beta over tau multiplied by omega. So now the current at beta is equal to 0, so this is V maximum over Z sine beta over minus theta plus sine theta e minus beta over tau omega. So to find beta, this one will cancel due to the 0 here, so it will be sine beta minus theta plus sine theta e minus beta over omega tau equal to 0. And this equation can only be solved using numerical solutions. Now I will solve an example for this with RL load, where the resistance of the load is 100 ohm, the inductance of the load is 0.1 Henry, the frequency is 60 Hertz of the supply, the maximum voltage is 100 volt. Number 1, find an expression for the current as a function of time, and since I of t in our load is V maximum over Z sine omega t minus theta plus sine theta e minus t over tau. So Z here will be equal to the square root of 100 square plus omega L square, which is 2 pi multiplied by 60 this is omega multiplied by 0.1 whole square, and this will gives me 106.7 ohms. Theta, on the other hand, is equal to tan inverse omega L over R, so this will gives me tan inverse 2 pi multiplied by 60 multiplied by 0.1. This gives me XL over R, which is 100. Then theta will equal to 20 degree 0.65. So the current as a function of time will equal to V maximum V maximum over Z, which is 0.937 multiplied by sine omega t minus 20.65 plus 0.353 E minus 1000 T ampere. B, they want us to find the average current, and the average current I average is equal to 1 over t integral I of t dt from 0 up to t. And since the current will equal to 0 when it reaches beta, so it's from 0 up to beta I of t dt. So now we have to find beta. And to find beta, we use the equation that is sine beta minus theta plus sine theta E minus beta over tau omega. So if I plugged in what I have, minus 0.36 in radian, theta in radian, plus 0.353 E minus beta over tau multiplied by omega will give me 0.377. So using a numerical solution, I used TI 89, which is Texas Instrument calculator, and the numerical solution tends to give me P1 equal to 3.5 radian, beta 2 is 6.65 radian. Since beta is greater than pi and less than 2 pi, which is greater than 3.14 radian and less than 6.28, I will choose beta 1. So B1 is selected, which is 3.5 radian. How I did find beta 1 in using the TI-89 is simply by using press F2, then select solve. From solve, just write the equation in terms of a variable, for example x minus theta, which is 0.36 plus 0.353 multiplied by e to the power minus x divided by 0.377, then equal to 0, comma, the x variable and then close the bracket, press enter, and you will get these solutions. So select 3.5 because it's in the appropriate range of beta. Now the next thing needed to be found is the average or DC current. The DC current component of this half-wave rectifier can be found by integrating the function from 0 to beta I of t dt. So using TI 89, I will press integral sine x minus 0.36 plus 0.353 e to the power minus x divided by 0.377, close the bracket, and then close the second bracket, then follows comma x comma from 0 comma up to beta, which is 3.5. Then close the integral bracket and press enter. So we will get IDC is equal to 0.308. Also I don't want to forget it's 1 over 2 pi here, and I don't want to forget also it's 0.937 from this expression. Number C is find the Rms current on the output side, which is actually equal to I input source Rms. So the Rms current is equal to square root of 1 over 2 pi from 0 to beta I of t squared dt. So we will square root 1 over 2 pi integral from 0 up to 3.5 0.937 squared, or it's better to write it this way, sine omega t, which is 377 t minus 0.36. we write it in radian, it's better, plus 0.353 e to the power minus t over tau, which is 0.001. This is whole squared, and we can square this one as well. So using TI calculator, the RMS current is 0.474 ampere. And then this question finally asked about the power, which is I output RMS squared multiplied by R. So it's 22. The answer is 22.5. Yeah, there is also another thing that this question asked about, which is the power factor. So the power factor here is 22.5 divided by the maximum value of the input voltage divided by root 2. This is the RMS value, multiplied by the RMS current, which is 0.474, and the power factor is 0.671, lagging power factor. So in the next lecture I will talk about full wave rectifier. So stay tuned. Thank you.